Good morning, students. Welcome to our online video class of Sri Gokulam Public School, Guruvayur. In previous section, we had discussed about isotopes, isobars, isotones, and what is atomic number and mass number. Today, we will discuss about wave nature and particle nature of electromagnetic radiation and also planetary model of atom. We have studied about Rutherford atomic model and also its drawback. Rutherford atomic model is also called planetary model of atom. Nuclear model of an atom can be compared with the solar system. Nuclear model of atom is Rutherford atomic model, which we can compare with the solar system. In an atom, the electrons are revolved around the nucleus like planets revolve around the sun. The nucleus represents the sun and the electrons represents the planets. Therefore, this model is also refers to as planetary model of atom, and the electrons are called planetary electrons. The results which observed historically from the study of interactions of radiation with matter have provided immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr's model of atom. The two developments are dual character of the electromagnetic radiation, which means the radiation possesses both wave-like and particle-like properties, and experimental results regarding atomic spectra. At first, we are going to discuss about dual nature of electromagnetic radiations. In the mid-19th century, physicists actively studied absorption and emission of radiation by heated objects. These are called thermal radiations. They try to find out what the thermal radiation is made. And it is now a well-known fact that thermal radiations consist of electromagnetic waves of various frequencies or wavelength. It is based on a number of modern concepts which were unknown in the mid-19th century. The first active study of thermal radiation laws occurred in 1850s, and the theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed in the early 1870s by James Clerk Maxwell. James Maxwell was the first to give a comprehensive explanation about the interaction between charged bodies and the behavior of electric and magnetic fields. Electromagnetic radiations. In 1856, J.C. Maxwell proposed that light and other forms of radiation propagate through space in the form of waves. These waves have electrical and magnetic field associated with them, and therefore these are called electromagnetic radiation. And Maxwell suggested the wave nature of electromagnetic radiation has when electrically charged particles moving under acceleration, alternating electric and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves. These waves are called electromagnetic waves or electromagnetic radiation. These are the radiation associated with electric and magnetic fields. Example is light. Light is the form of radiation known from early days. In earlier days, Newton had suggested that light was composed of small particles called corpuscles, and the corpuscular theory had dominated mainly because of Newton's scientific reputation. The thought processes of the scientists throughout the 18th century. However, at the beginning of the 19th century, experiments demonstrating the diffraction and interference phenomena of light firmly established the wave nature of light. Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. The figure shows an electromagnetic radiation wave. In this, the electric field and the magnetic field oscillate in perpendicular planes. These components have same wavelength, frequency, speed and amplitude, but they vibrate in two mutually perpendicular planes. The important characteristics of those radiations are all electromagnetic radiations are associated with the oscillating electric and magnetic field at right angle to each other, or the oscillating electric and magnetic field are perpendicular to each other and both are perpendicular to the direction of propagation of the wave. And the electromagnetic waves do not require a medium for the propagation and can move in vacuum. These radiations travels with the same velocity equal to that of light in vacuum, that is 3 into 10 to the power of 8 meter per second. This velocity is represented by c. There are many types of electromagnetic radiations which differ from one another in wavelength or frequency. Electromagnetic radiations are described in terms of any one of the parameters such as wavelength, frequency, wave number, etc. And these constitute electromagnetic spectrum. In this figure, A represents the spectrum of electromagnetic radiation and B is the visible spectrum. The visible region is only a small part of the entire spectrum. The arrangement of different types of electromagnetic radiations according to the increasing wavelength or decreasing frequency is known as electromagnetic spectrum. The different regions of electromagnetic spectrum are arranged as cosmic rays, gamma rays, X-rays, UV region, visible region, infrared region, microwaves, radio waves, etc. We can represent electromagnetic radiation in different units, or electromagnetic radiation can be described in terms of different parameters. Such parameters are frequency, wavelength and wave number. Frequency, it is represented by nu. It is defined as the number of waves that pass through a given point in 1 second. The SI unit of frequency is Hertz. Hz or second inverse. And wavelength, it is the distance between two adjacent crust or two adjacent trough. Its unit is meter or centimeter. Another parameter is wave number. It is represented as nu bar. It is defined as the number of wavelength per unit length. It is the reciprocal of wavelength. Its unit is meter inverse or centimeter inverse. The frequency nu, speed of light and the wavelength lambda are related to each other as C equal to nu lambda. Next we are going to discuss about Particle nature of electromagnetic radiation. Planck's quantum theory. Some of the experimental phenomena such as diffraction and interference cannot be explained by the wave nature of the electromagnetic radiation. Wave nature of electromagnetic radiation failed to explain certain phenomena such as black body radiation, that is the nature of emission of radiation from hot bodies, and photoelectric effect, that is ejection of electrons from metal surface when radiation strikes on it, and variation of heat capacity of solids as a function of temperature, and line spectrum of atoms with a special reference to hydrogen. And the classical physics failed to explain these phenomena. The quantum theory had its origin in 1900 with Max Planck's attempt to explain the black body radiation. Black body radiation. The term black body refers to an object which is a perfect absorber of all frequency of radiation falling on it. Hot objects emit electromagnetic radiations over a wide range of wavelength. At a high temperature, an appreciable proportion of radiation is in the visible region of the spectrum. As the temperature is raised, a higher proportion of short wavelength, that is blue light, is generated. For example, when an iron rod is heated in a furnace, at first it becomes dull red, then progressively become more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. This means that red radiation is most intense at a particular temperature and the blue radiation is more intense at another temperature. And this means intensities of radiation of different wavelength emitted by hot body depends upon its temperature. An ideal body that emits and absorbs radiation of all frequencies is called black body. The exact frequency distribution of the emission from a hot black body depends upon temperature. In practice, no such body exists. Carbon black approximates fairly closely to black body. A good physical approximation to a black body is a cavity with a tiny hole which has no other opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. That is shown in this picture. This figure is a black body. The amount of light emitted from a black body and its spectral distribution depends only on its temperature. At a given temperature, intensity of radiation emitted increases with the increase of wavelength, reaches a maximum value at a given wavelength and then starts decreasing with a further increase of wavelength. Also, as the temperature increases, maxima of the curve shift to shorter wavelength. The phenomenon of black body radiation was first explained by Max Planck by his quantum theory. According to this theory, atoms and molecules could emit or absorb energy not in a continuous manner but discontinuously in small packets of energy called quanta or photons. The energy E of quanta of radiation is proportional to its frequency nu, and it is expressed by the equation E equal to h nu, where h is known as Planck's constant and its value is 6.626 into 10 to the power of minus 34 joules second.